Today we begin our day with a focus on the theme of carbon capture. And our keynote speaker for today, this morning, is none other than Professor Rajnish Kumar from IIT Madras. A thought leader in this field, Professor Rajnish, we eagerly await your insights.
I'm going to talk about CO2 capture and sequestration, but before I talk about that, let me give a small disclaimer that whatever I am going to tell you today, it might look little pessimistic, but I am just trying to give you the data, so please don't shoot the messenger. What I am trying to focus today in my today's talk is that whatever we talk about transition of energy, whether we are going for solar, we are going for hydrogen-based economy in future, we have to always keep sustainability in our mind because this is what we have not done so far. And we see today in India, around 3 billion tons of CO2 is being emitted every year. Around the world, you know, the last year data was 41 billion CO2 emission in 2023. Okay, so moving on, we have been really poor in predicting how much CO2 emission basically we would be doing in future. So this is a data of 2018, and at that time it was predicted that by 2020 we are going to peak. So by 2020, the CO2 emission will be the maximum CO2 emission we will see, and after that there will be a drop in CO2 emissions. This was predicted based on the kind of policies were implemented around 2018. But then most of those policies we were not able to really implement it properly, and this is why you see we have not really peaked. Even in 2023 was the largest CO2 emission we have seen so far, and it's expected that this is not going to peak for next 2-3 years. And some of the predictions suggest that we will have a peak at around 2030. So that is something which is a big concern. If we are going to peak at around 2030, it basically means that this 1.5 degree target we have been talking about, we are not going to basically attain this target. Because the budget which we have right now is around 250 billion tons of CO2, and we produce around 41 billion tons every year now. So in 5 to 6 years' time, we would basically breach that 1.5 degree target. And I don't really see any commercial plant which has been projected to start capturing most of their CO2. So that pretty much tells you that 1.5 degree target we are not reaching. That is something which is the reality now. Now, if we have to attain this target of 2 degrees, that is the rise of 2 degrees compared to pre-industrial level, we have around 1150 billion tons of budget. Okay, so that typically means that we have another 20 to 25 years to basically meet this particular target. And in next 20 to 25 years, we'll have to basically scale up. We have to ramp up significantly so that we meet this target. Otherwise, we are going to miss this target as well. Because we have been talking about CCUS or other source of energy from fossil fuel based to renewable, but we have not really met any of our targets so far. I'll tell you, if we have to rely on CCUS, that is carbon capture, utilization, and sequestration, we will have to decarbonize our industry. It has to be done through CCUS and also through other means. For example, if you are talking about power industry, which is the largest emitter of CO2, it is projected by 2050, we should be able to move almost 60 to 70% of fossil fuel-based power generation to renewable-based power generation. Remaining 17 to 18% of CO2 emission cut is going to come from CCUS, and then we will probably ramp up our nuclear production and nuclear to electricity production to basically meet the target of around 300 gigaton carbon dioxide cut through for power generation. See, let me be very frank with you in this. Most of the power generation, the way we use our energy is we use the fossil fuel energy as a heat source, and then we convert heat source into electricity. What we are proposing when we say renewable, we are proposing to go extremely to the other side. We are now going to produce electricity, and then as far as all the processes, I'm a chemical engineer, so as far as all the processes are concerned, when you talk about industry here, CO2, cement manufacturing, steel manufacturing, most of this industry uses heat. It does not use electricity as of today. So as a chemical engineer or as a process engineer, you have to also worry about how do you basically help transition the industry from utilizing heat as a source of process to electricity. So this is going to be a big challenge. Today, or say till last decade, we have been talking about in chemical industry moving from batch-based processes to continuous processes. Okay, we have not even done that completely. Now we are talking about moving from a process which basically utilizes heat as the primary energy source to electricity as a primary energy source. So the change of process is going to be significant. But what I was trying to tell you here, that renewable energy plays a significant role in power generation. This is what is basically predicted by many agencies have talked about it. While it comes for industry, if you see here, energy efficiency has to play a significant role, because industry, at least by 2050, you are not going to see green steel and green cement. It's predicted by that by 2045, probably we will be starting to see significantly large portion of green steel and green cement. But by 2050, if we have to basically cut down so much of CO2, it has to mainly come from energy efficiency improvement. In transportation sector, again, we have to switch to renewable. There is a large section from batteries, and then again you will have to improve the energy efficiency in transportation sector as well. These are some of the major source of CO2 emission. Buildings, people talk about green buildings. Again, here you see you will have to switch the fuel as well as you will have to go into energy efficiency. And other transformation where again everything depends on energy. So if you see, the common theme over here is that you have to rely completely on the way we utilize our energy and improve our energy efficiency. And when it comes to power sector, it has to be completely renewable. So these are some of the data which basically has been presented. But when it comes to renewable, how India is doing, if you look into 1985 to 2022, the current data, you see we have not improved. We are almost stagnant. So we have been talking about utilizing renewable energy for a really long time, but our renewable energy percentage, which basically we use in our day-to-day life, has not really increased. And this is not only biomass, it's hydropower, solar, wind, biomass, waste, geothermal, all put together. So it's not that we have been really utilizing our renewable sources that effectively. Either we have not really ramped up our installations, or we have not been really serious about moving to renewable energy. And because of this, you see the CO2 emission in India has been increasing at the rate of 7% every year. So today, last year, the data is that 2.9 billion tons of CO2 was emitted. And with 7% rise, if you basically do a proper calculation, by 2030 or 35, we might be seeing a number of around 5 billion tons to 6 billion tons of CO2 per year if we don't do anything about it. Now, the rate at which the solar panel which are being basically installed in India, which is the prime electricity source which we have been talking about, renewable electricity source, is rising at around 6% per year. So basically, what I am trying to tell you is that this rate at which CO2 emission is going to happen in India for next decade or couple of decades is not going to really taper off. We are going to significantly produce large amount of CO2. Right now, we are third in this particular list of CO2 emitter countries. First being China, which produces around 11 to 12 billion tons of CO2 every year. The second is USA, which produces around 5 billion tons of CO2 every year. And the third in the list is India, which is around 3 billion tons of CO2 every year as of today. So, and this is rising at the rate of 7%. This year, 2023, it rose at the rate of 8%. So it's not that it is tapering off, we are actually increasing, and this is kind of expected because we are still developing. Now, when we talk about renewable, we mostly focus in India on solar. So once you talk about solar, solar is only available during the sunshine hours. Post the sunshine hours, you'll have to worry about storing the solar electricity. Now, if you are talking about moving to hydrogen-based economy, why hydrogen-based economy is very important compared to electric or batteries, I'm going to talk about that today. But let's see how efficient is this hydrogen-based economy. Okay, I'm not going to talk about batteries because there are other sessions for that. So if you talk about hydrogen, it's an energy carrier in this particular case. You would produce around 55 kilowatt of electricity from a solar panel, and if you use that electricity in electrolyzer, you are going to produce 1 kilogram of hydrogen. So for producing 1 kilogram of hydrogen, you basically need around 55 kilowatt of electricity. Okay. Now, what you are going to do with this hydrogen, it's an energy carrier. You may basically burn it, you will use it in a fuel cell. So if you use it in a fuel cell just right beside your solar panel, you will get back 30 kilowatt hour of electricity. So you are losing, converting this electricity into hydrogen and then back to electricity around 25 kilowatt hour, or roughly 50% of your electricity you have already lost here. Now, if your hydrogen has to be transported, stored for longer period of time or transported to a long distance, you are going to basically kill another 10 to 15 kilowatt hour of electricity to transport 1 kilogram of hydrogen, depending upon what technology you are going to use, how far you are going to transport it, or how long you are going to store it. So if you see this particular data, basically there is a shortfall of roughly 40 to 45 kilowatt hour of electricity. So basically, if a solar panel is producing 55 kilowatt hour of electricity, it's not that entire electricity you are going to get. If you have to rely on batteries, you will have to install thrice as much, because let's assume 6 hours is the sunshine hours. So if you are going to use it for 24 hours, you will have to install thrice as much capacity. Hydrogen is also very similar. It's not that hydrogen is better or batteries are better. But why hydrogen is more important is what I'm going to talk about in next slide. Hydrogen is important because even for CCUS, you need large amount of hydrogen. And requirement of hydrogen, today hydrogen, or in future hydrogen will become one of the prime commodity. Every industry would need hydrogen, because if you are not going to get your hydrogen from fossil fuel, because hydrogen, the prime source of hydrogen and carbon is from fossil fuel. If we suggest that we are not going to use any fossil fuel for our source of as a source of hydrogen, then the only source of hydrogen will be this, electrolysis of water. And if electrolysis of water is the only source of hydrogen, hydrogen is not only required as an energy source, it required as a chemical commodity throughout. So hydrogen requirement is going to be significantly large. And this is one of the reasons why you will see, if someone tells you that we are going to bring down the cost of hydrogen significantly, this will be a challenge. You cannot bring down the cost of hydrogen significantly, because this is what thermodynamics tells you pretty much. You cannot get better efficiency from a fuel cell than what you are already getting. Maybe 1%, 2%, 3% rise of efficiency you can get. But the cost of hydrogen is not going to come down significantly, or at the rate at which most of the time people talk about that it will become 50 rupees per kg or 100 rupees per kg. It's going to be really difficult for you to do that, because the electricity generation cost will have to come down significantly for that to happen. So that is something which one has to always understand. So what I was trying to say, that use of hydrogen is going to be very important, because even if you talk about CCUS, what is CCUS? CCUS is capture of CO2 either from point source or directly from the air. Now, when it comes for capture of CO2 from point source, it's much easier for you to capture CO2 from point source. The prime reason is because the partial pressure of CO2 is much higher over there. Or in other words, the concentration of CO2 is much higher over there. One CO2 molecule is surrounded by roughly around 10 nitrogen molecule around it. Let's assume that the only other gas is nitrogen. Obviously, there are many other gas, but for just simplification, for understanding, we say that roughly 10 to 15% CO2 is part of any flue gas operation, and flue gas comes typically when you burn a fossil fuel for your energy need, and you will have to burn it in excess of air, so you will have a lot of nitrogen and oxygen along with CO2 after the combustion process. So typically it's around 10 to 15% of CO2, remaining being nitrogen, oxygen, and some of the SOx, NOx, and other stuff. So right now those are being captured, SOx and NOx. CO2, nitrogen, and oxygen are being released to the atmosphere. So the point source which we talk about over here is roughly 10 to 15% CO2, remaining being nitrogen and oxygen. It means for every CO2 molecule, there is roughly 10 to 15 nitrogen molecule. So if you have to bin one CO2 molecule from 15 nitrogen molecule, it's much easier for you to do that by any material. Okay, basically this material will have to capture this CO2 from the other nitrogen molecule. So the material has to be exotic, but not that exotic, because it has to do its purpose. It has to bin one CO2 molecules out of 10 to 15 nitrogen molecule around it. But when we talk about directly capturing CO2 from the air, there the concentration of CO2 is only 410 ppm as of today. So basically you are talking about carbon dioxide capture with other gases, which is primarily again nitrogen in air. So out of one molecule of CO2 out of 2500 molecules of nitrogen. Okay, so you can imagine in this particular room there is not even 2500 seats. So if you imagine that there are 2500 seats over here, and if there is only one carbon dioxide sitting over here, I need a material which has to be very exotic. We'll have to go and catch that particular guy. It means this material, exotic material, has to be synthesized with multiple steps. Okay, I don't want to go into too much of detail, but this exotic material has to be synthesized, that has to be kept in mind. And when we are talking about 3 billion tons of CO2 every year, I will give you a data. In this particular data, if you see, it's not, I don't want you to read, but what I want to tell you is that typically any good material will capture either 0.1 gram of CO2 per gram of this material or 1 gram of CO2 per gram of this material. This is the best you can get actually. So what I'm trying to tell you is that if I have to capture 3 billion tons of CO2, I need 3 billion kilogram of this particular material, which has to be recycled 100 to 1000 times. So what has to be the focus for the researcher? The focus should not be on the capture capacity, rather on the recyclability. Because if I'm not able to recycle my material, it basically means that the CO2 which was emitted during the formation of this material will not be able to capture even that much CO2. Okay? For example, I'll give you a data. 1 kilogram of hydrogen, if you produce black hydrogen, gray hydrogen, which we call today, if you produce 1 kilogram of black or gray hydrogen today, you emit roughly 15 to 20 kilogram of CO2. So just imagine any other material you are going to produce. We say steel you produce, it produces 1 ton of steel produces around 3 tons of CO2. So any material which you are going to produce, any exotic material over here, any material of character which is metal organic framework or other geolite, it basically means that if I am going to produce 1 kilogram of this material, it will at least produce 5 to 10 kilogram of CO2. So this material should be at least be recyclable 10 times to capture the CO2 which is being produced by itself while this material was being generated. So this has to be the focus. Recyclability has to be focused, because this material has to not only capture the CO2 which was produced during the production of this material, but also all the CO2 which is being produced by transportation industry, by power industry, by industries like cement and steel and all. So basically it means I need a very robust material which could be recycled 1000 times or 100 times. So no exotic material as of today can be recycled 100 or 1000 times. Most of these materials we talk about has been hardly tested for 10 times, 15 times. So this is one challenge which one has to always understand. There is other material which industry talks about. How much time do I have? Am I running out of time?
I think you're good for another 5 minutes.
Okay. So if you talk about the other process, so the last slide which I talked about was typically academician's work which will get published. But when you talk about industry, you will see that industry talks about monoethanolamine as the material which will use to capture CO2. Okay, monoethanolamine or a derivative of that, it will be or many other combination of these materials and all. See the challenge again, what I was trying to point out that why hydrogen is essential even for CCUS. See, monoethanolamine, again, if I am going to capture 3 billion tons of CO2, I need that much amount of monoethanolamine to be produced. Even if it is getting regenerated, I'll tell you, there is for every ton of CO2 captured, 2 kilogram of amine gets lost. Gets lost means you cannot regenerate it. Okay, there will always be those reactions which will not allow you to basically regenerate these molecules. So now monoethanolamine has to be produced. Today you are not producing it because you are not capturing the CO2. So if you have to produce monoethanolamine to capture that large quantity of CO2, where it will come from? It will come from the reaction between ammonia and ethylene oxide. Okay. Now ammonia today, which you are going to use ammonia, is not green ammonia. Basically when I say green ammonia, it's not ammonia which is produced by green hydrogen. So ammonia itself has a CO2 footprint. Ethylene oxide, right now the only source of ethylene oxide is fossil fuel. So if you don't want to use fossil fuel, it means basically you would need hydrogen here. You will need hydrogen over here so that you can produce your monoethanolamine. Because if you don't produce this, you cannot capture this CO2 which comes from the power plant as of today. So CCUS, as we know today, is not only a carbon dioxide capture process, it also relies heavily on hydrogen generation. If you cannot produce hydrogen at an effective cost, today we talk about the cost of CO2 capture from point source is $50 per ton. For 3 billion tons of CO2 which India produces, you see the cost which will be required to capture all that CO2. This is not a challenge. The bigger challenge is today the cost was calculated based on black ammonia and black ethylene oxide, not with green ammonia and green ethylene oxide. So if you are going to produce green ammonia and green ethylene oxide, you can imagine the cost of this molecule. And if you are going to lose so much, what will be the cost of CO2 which is being produced from this? Now the next step is that once you have captured the CO2, what you are going to do with that CO2? So the proposal is that I am going to convert this CO2 into methanol, into ethanol, into DME and all kind of things. Again you need hydrogen because the only other commodity which is required you to basically convert this CO2 or utilize this CO2 is hydrogen. So hydrogen is not only required in the capture process, now once you have captured it, it is also required during the utilization process because every CO2 molecule has to react with multiple hydrogen molecules to produce any other commodity which we talk about. So now the question is, if CO2 comes at around $100 per ton with green ammonia and green ethylene oxide, and if hydrogen comes out with around $200 and $250, $300 per ton, and this is the cost from the point source, what would be the cost of the product which we are going to sell, whom we are going to sell this particular product? At $500 per ton, who is going to buy your stuff? So these are the challenges. Economy has to always come into picture when we do this kind of process calculations. I will just last 1 minute. I will just show you one largest direct air capture unit. By the way, direct air capture costs around $200 to $300 per ton. This is much more expensive. Now this particular plant is the largest in the world, and I'll just show you one small data. This is equivalent to 1 second of global CO2 emission. This is the largest plant as of today, 1 second equivalent of global CO2 emission. This is another largest plant of utilization of CO2, and this plant is equivalent to 2 minutes worth of CO2 emission. 160,000 tons of CO2 to methanol or ethanol, whatever you want to produce. So there are a lot of challenges. In our lab, we keep working on it. Means I am saying that all this is true, still we work on it because we have to identify a solution. There is nothing you can do about it. So we have multiple processes which I do not have time today to talk about. So, and this is not working. Yes, fine. I'm just going to go to the final slide, and thank you.